In this problem, we're given this set of matrices, described like this, right? So these are 2 by 2 matrices in which the diagonal is 1. There's 0 always here, and here there's always an integer, any integer, right? So that describes the set, and we have the standard matrix multiplication in this set. And we're asked to prove that this is a group, and we need to describe what is the identity and the inverse of any element in this group, and to check whether this is commutative or not. Okay, let's see. First, we're going to multiply 2 elements of this set. So let's say that we have one n01 and one m01, right? And we multiply them out. If you make the matrix product of this is just, well, this is this first element, okay, and this one here, what it says is that we have to add these 2, right, and here we have 1. So what we get is another matrix in which there are 1s in the diagonal, 0 here, and here there's an integer, because if n and m are integers, this is also an integer, so this belongs to m, so the product is closed in this set, right? Okay, now let's see associativity. Well, associativity is guaranteed, right? This is G1. Associativity is guaranteed because matrix product is associative. G2 is the identity, and well, the identity here is easy to figure out. It's just the matrix 1 1 0 1, which of course 0 0, which of course belongs to m, because 0 here is an integer, right? So we have identity 2. And for the inverse of every element, well, let's say that we have this element and we have to figure out what m should be for this to be the identity. Well, obviously, what we have to satisfy is this equation. So m is equal to negative n. So given an element 1 n 0 1, the inverse of this element is 1 negative n 0 1. So every single element of this set has an inverse, right? So the inverse is guaranteed, so we have a group. Not only that, we can check commutativity, and commutativity is guaranteed because this operation m plus m is commutative. So it doesn't matter the order in which we make this product, we get the same matrix, so it's also commutative. So we have a commutative group, an abelian group. This is an abelian group. And as a matter of fact, this group is isomorphic to, this group here is isomorphic to the integers with addition. Because you can associate any matrix like this to one integer. And the integer is, of course, the integer you have to put here. And the operation between these two matrices, the product of this, is just is the image of the image of the sum of these two integers here. So you have this isomorphism. So you have a matrix, a function, sorry, that maps this matrix into n. So that's a mapping from n to z, right? Which, of course, respects the product. So if you have here the product of these two matrices, right? Since the product of these two matrices is just this matrix, so it's equal to f of 1 m plus m 0 1, and that gives you m plus m, all right, which is just n is the image of this 1 n 0 1, right, and m is the image of this 1 m 0 1. So you see, you have that the image of a product with the product of the first group is equal to the product of the images with the image with the product of the second group here. So this is an isomorphism. And actually this is a bijection, right? Because given n, you can recover easily the matrix it comes from, and different matrices have different images. So so this is a bijection which respects the product. So it's an isomorphism. So these two groups are isomorphic.